Okay, so welcome to the next NPTEL live interactive session for the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning. This is a course offered by Professor Aditya Jagannatham from IIT Kanpur. So a little bit about myself. So my name is Yashvanth and I'm presently a PMRF Ph.D. research student with the Department of EC at IISc Bangalore. So my research advisor is Professor Chandra Murthy, who is also with the Department of EC at IISc Bangalore. My broad research interests lie in statistical signal processing and applications to wireless communications. My current focus in the PhD is on intelligent reflecting surfaces for 5G and beyond wireless communications. You can always feel free to write to me at this email ID yashvanth.l at the rate of iisc.ac.in, and you can always know more about me by clicking into this particular link. So the topics which will be covered for today's session will be based on optimal power allocation in MIMO systems and some direction estimation problems. So as usual, the first part of the today's TA session will be to quickly summarize the week 7's lecture. Um, the first lecture started with the title MIMO optimization. In the last TA session, we went through this concept of spatial multiplexing. So spatial multiplexing is a system, is a technique in which if you have multiple antennas at the transmitter, let's say NT antennas at the transmitter, and if you have a receiver with NR antennas, then what are the number of parallel channels or parallel streams that you can form between an NR cross NT MIMO system? And it turns out that you can form rank of h number of independent streams between the transmitter and receiver, where h is the channel matrix of size nr cross nt. H is a channel matrix. H is channel matrix of size nr cross nt. So we illustrated that if you have a transmit symbol xi, it will undergo a gain, which is basically the gain is given by the ith singular value of the matrix H, and then it undergoes a noise addition, and yi is the receiver output. And like this, you can have rank of H number of independent channels. So this is called spatial multiplexing. That is, you multiplex different information symbols over um, non-interfering independent channels. Note that these independent channels are arising out of the spatial dimension. That is, we have merely made use of the singular value decomposition of the matrix H in order to create rank of H number of independent streams. Okay, so that is called spatial multiplexing. So we saw in the last session, also introduced by Professor Aditya Jagannatham, that the rate achievable from this kind of a system per given bandwidth per given bandwidth. That is, generally we talk about 1 Mbps or 10 Mbps or 100 Mbps. Mbps stands for megabits per second. That what is mega? So if I say 1 Mbps, that means essentially I'm saying 10 power 6 bits per second, right? So this mega is captured by the power 6. Now this is actually, if you see, this is actually obtained as 10 power 6 into 1 bps. This 10 power 6 is really the bandwidth. That is, whenever you allot a particular bandwidth to a transmit symbol from one place to another, that will also multiply the rate. So as you keep increasing the bandwidth of communication, your rate will also keep scaling up. Now, if I divide by per bandwidth, what is left? It's just 1 bps. That is, in 1 hertz of frequency bandwidth, what is the amount of data that I can send over a channel? So that is what I'm measuring now. So I'm call that as rate per given bandwidth. Okay. So if you see that I did not multiply by b in the expression for rate. That's why I'm saying this is the rate per given bandwidth. Okay. So that is for any spatial multiplexing based system, it's given by summation over all the streams. It's sum over all the streams times the rate achievable per given bandwidth in a given stream. That is log base 2 1 plus SNRI, where SNRI stands for the signal to noise ratio in the ith stream. And like that, you have rank of H number of streams, right? And last time we also showed. So what is signal to noise ratio? The signal power divided by the noise power. So if you see this particular yi, yi can be written as sigma x plus ni. So this is the signal power and this is the noise power. So what is the signal to noise ratio? This power in first term divided by the power in second term. What is the power in first term? It's just sigma I square times power in the x. That is the basically this the power in the x is given by pi. That is the power allotted to the ith data symbol. Okay, pi is the power of xi. Okay, and sigma square is basically the noise power, and the sigma I square is a channel gain that multiplies here, so it just gets squared up and multiplies with pi divided by sigma square, right? So now this is the achievable rate. You see, the sigma I square is the singular value of sigma I is the singular value of the channel matrix. And what determines channel matrix? That is nothing is under our control. The air channel that we see in the environment is nature given. So you really don't have control over the singular values of the channel matrix. But what is really under, similarly, the rank of the channel is also not under our control. That depends on the environment, how the wave propagates in the environment. Sigma square, noise. Noise is also something it's not under our control, because noise is something which is undesirable and that gets added out of because of the impairments in the system. The only quantity that is under our control is the pi. That is the power. What power do you want to mount your symbol up to? Do I want to scale my symbol to 1 kilowatt, 1 watt power, or is it maybe 0.1 watt? What is the power? That is something that we can choose. That is at our control. So basically, if I want to maximize the rate of the system, any ideal communication system, I would want to maximize the rate. So the optimal power allocation problem is basically to find set of P1, P1, P2, and so on till P rank of H, because there are rank of H number of streams. There are these, so there are as many as powers as rank of H. So basically, the optimal power allocation problem is I want to figure out all the optimal power allocation coefficients. What is the optimal power that I will allot to the ith stream, such that this sum rate is maximized. But it is not completely, just this is a part, but we also have a constraint that, because power is also in some sense a natural resource, we would not want to give more power to all the system, because that will, we also want to maintain some kind of energy efficient system. For example, if we are all using mobile phones, we don't want our mobile phones to emit a very large power, else there are so many health issues that we may run under easily. So we always want to maintain a maximum power that my mobile can generate. Okay, now given the maximum power, given the constraint that I have only a power budget of P total, what is the optimal power allocation across the streams so that my net sum rate across all the streams is as maximum as possible? This is called optimal power allocation problem. Okay, and professor had derived the solution for this optimization problem. This is a constrained optimization problem, because I'm not just interested in maximizing the quantity. Also, I need to ensure that the solution to the maximization problem satisfies the constraint. That is, what is the constraint? Sum of all the power allotted to all the streams must be at max the power budget that I have at our hand, right? So the solution to this kind of a problem is attempted by using the Lagrange multiplier method. The final solution takes of this form. So Pi, that is the power allotted, I will just put a superscript. So if I say a star, that means there is an optimal. Pi star means the optimal Pi for the ith string. Okay, so Pi star is given by this particular term, 1 by lambda minus sigma square divided by sigma I square. See, sigma square is a noise variance and sigma I is the singular value of the ith stream, or in some sense this is basically sigma I square, not sigma I, right? Just a minute. Okay, this is supposed to be sigma square, not sigma. Yeah, it's supposed to be sigma square, sigma I square, just not sigma. Okay, so basically, so in some sense the sigma I captures what is sigma I. The sigma I basically, it is a channel gain for the ith stream, because that is what the transparent symbol is getting multiplied. The channel gain, the effective channel gain maybe in the ith stream. Okay, that is the effective channel gain in the ith stream. So now you see sigma square divided by sigma I square. Okay, power, it's not power, but I have a plus operation, meaning that power cannot be negative. Power is always a positive quantity. In case the optimization problem is the returns pi star for some I is a negative number, let's say -2. What that is just mathematics. Mathematics will not always capture physics, right? So what generally, why do we use mathematics for engineering? We have some kind of a system and we try to model that system using some mathematics, and we solve it using mathematics and translate it back to engineering again. That is the utility of mathematics in engineering. So now if I say pi star equal to -2, I cannot say that I have to put -2, watt for this particular stream. So physically what it means is I will just not put any power in that particular stream. That should be your engineering solution. That's why to incorporate that fact, I use a plus star, meaning that if this 1 by lambda minus sigma square by sigma I square turns out to be a positive number, retain that number as it is. If it turns out to be a negative number, just make it 0. That is that. So the operator x plus is defined as max of 0 comma x. Whenever x is positive, x is greater than or equal to 0. So max of 0 comma x is same as x itself. But whenever x is negative, max of 0 comma x will be 0 itself, because x is negative number. So this plus will ensure that pi is always a positive number. Okay, and okay, so pi, I know what sigma square is, I know what sigma I square is. Okay, how to find 1 by lambda? What you need to do is you need to use this. You need to use the power constraint. That is, see this, but this particular expression does not have any p total, which is the total power constraint. So make use of the power constraint equation in order to find the 1 by lambda. That is what is the, namely that summation over all the pi star should lead to p total. Okay, maybe I will write that also here. So this is pi star. Summation over all pi star over all I equal to 1 to rank of h should equal p total. So substitute all these, and then use this equation to determine what 1 by lambda is. Okay, so now there is a very beautiful interpretation of this particular kind of an optimization problem. So if you understand this particular, interpretation, pretty much the entire solution will be well understood.
Sir, can you tell more about that plus sign that we use, sir?
Okay.
Yeah.
So what this plus sign stands for is basically it will, if this number, let me maybe give an example. So if I have 2 plus, that is a number power, it's not power, it's just an operator. 2 plus is same as 2. But if I have a -2 and take a plus operator, it is same as 0. That is what I'm trying to say is whenever the number is a positive number, then the output of this operator is the number itself. But whenever the input number to this operator plus is a negative number, the output is 0. Okay. So this particular operation is captured by plus. The reason is power cannot be negative. Power should always be a non-negative number. It can be 0, but it cannot be less than 0. That is the reason we include this plus operator. Okay. So yeah.
Pi star.
What is the say arg of maximum? This term you have used many times, but what do you mean by that? Yes, arg, arg.
Okay, fine. It's a notational question. So see, this max of this quantity, right? Max of this quantity will give the maximum value that this particular number can take. But at what values of pi will this be maximum? That is argument of the maximum value. Argument here is what the optimization variable pi. That's what I'm writing, argmax pi. With respect to what argument pi will this maximum be attained? So that means the output of this argmax is the argument. That is a set of all pi's itself. But if I don't write argument, if I don't write this, if I write only this, then it will give the maximum rate that you can achieve. It will not tell what is the power at which this max rate is achieved. Okay.
Example, sir, because I understood, but please give one example of this arg.
Yeah, sure. Okay. Fine. Let's say I want to do argmax of x square, and x belongs to the range subject to the constraint. This is a constraint I'm giving. Subject to constraint, x lies between 0 to 2. This is the optimization problem. Okay. So the answer for this argmax of x square with respect to x, such that x lies between 0 to 2, is what? Let's see. What is the maximum value that x square can take if x lies between 0 and 2? 4, right? 4. But argmax will give you the answer 2. That is the x at which x square is maximum. Okay. X at which x square is maximum. But if I just write max of x square such that x lies between 0 and 2, the answer is 4. Because that is the maximum value x square can take. But if I write argmax, if I write arg, I should say with respect to what is the arg, that is x here. X is the argument. X is like the variable. Variable of optimization is what the argument will return, not the value itself. Right? So argmax, if I write, it is 2. Is this clear?
How it is 2?
Sorry?
Sir, how it is 2? You have to write 2. 2 is the maximum of xness, what it can take.
Correct. Okay. That's what I'm saying. Maybe I'm getting an echo. So what I'm trying to say is 2 is the value of x at which max of x square is possible. So if I write...
Okay, understood now, sir. Understood now.
Okay, let me give another example. Maybe to check whether this is fine. Let's say not x square. Maybe I will say sin x. Okay, and x lies between 0 to pi by 2. Okay, can you now tell me what is max of sin x subject to the constraint when x lies between 0 and pi by 2?
1.
Correct, 1. Now if I say argmax of sin x subject to x lies between 0 and pi by 2, what is the answer now?
5 by 2.
Exactly. Argmax means it will give the variable, the argument at which your maximum is attained. That's all. Okay. Fine. Was there any other question? Some other question?
One question, sir. Now we were solving this optimization problem to see what should be the power to be applied at individual transmitter stream. Then, but we didn't see any relationship with the phase here. So,
phase. That's a good question. See, why phase doesn't come? Phase means you mean that because H mat is a complex matrix, so every complex number will have an associated phase. Is that your logic to argue?
Yeah, when we talk about precoding, mostly we have both amplitude and phase, right?
True. Very good. It's a very good question. So the answer to this lies in two things. So you have actually hit a very fundamental question. The thing with power is, see, now if you look at the effective channel, see here the effective channel, this sigma I is a singular value, is no more a complex number. It is a real number because that is how the singular value decomposition is defined as. Every singular value is a non-negative real number. Our original channel was a complex channel, but we have done some pre-coding and pre-coding at the transmitter and combining on the receiver such that the effective channel, if you recall, we had transmitter, then we did something called pre-coding, then we had the channel, then we did something called combining, and then we have the receiver. If you take this effective channel, is what is this channel, right? This effective channel is no more a complex channel. It's just scaled by sigma I, which is a non-negative real number. Okay, so now every particular channel is something that is scaled by a real number, which for which the phase is a zero number. Okay, so that is one way to argue that the channel is no more a complex channel. Okay, now number two, about the pre-coding aspect. That's a very good question. In general, if you have x, okay, you will pre-code that with some w times x. If that is, let's say, x tilde is equal to wx, where x is the actual transmit vector. But you know, in most of the paper or most of the research community work or even industrial papers, if you read, what they do is they don't write W times X. They write root P times W times X such that the norm of W, for example, Frobenius norm of W is equal to 1. They captured the power allocation component separately as root P times the precoding vector W. If you want to call the effective as W dash, okay, that's the actual precoding vector. But if I want to normalize my weight equal to unit magnitude and add an extra term to denote the phase, then denote the power, then that basically is again a independent power allocation problem. Then the problem is, okay, what is the precoding vectors and what should be the optimal power allocation that I need to do? Spatial multiplexing, what is the answer? The optimal precoding vectors are the right singular vectors. And what is the optimal power allocation? This particular optimization solution. Is that clear?
So, okay, are you saying that when we have this precoding now, we don't need to consider phase?
No, precoding is still, you see, root P times W times X. See, precoding is still a complex matrix.
Right.
But I do not, but I take away all the power component as separate. So that's what I'm saying. If I write root P times precoding matrix times X, then I need to ensure that this precoding matrix satisfies the norm that it is equal to 1. It doesn't add any power on its own. The only energy in the transmitted vector comes from the root P. This will not add any power.
Okay.
So basically, the power can still be considered as independent of phase because I've abstracted out all of them into the precoding matrix W.
Still, we will have W component. Still, we have W component when we apply.
But that's what I'm saying. Now, the moment you have W component, that's what I'm saying. The moment you apply W component and the combining component, the resulting channel will become a real channel. And now the problem is to allot the power allocations for these set of parallel real channels.
Yes.
Yeah.
So the precoding eliminates the phase part in the channel.
Correct. Every precoding matrix is a complex matrix, so it will have its own phase. Every entry will have its own phase.
Okay.
Yeah.
Thank you.
Sure. So now, this particular power allocation problem has a very beautiful interpretation of what is called a water filling over a vessel. Okay. Now, maybe you forget about the optimization problem. Let me describe what this water filling over a vessel means. Okay. Consider that there is a vessel. I mean, okay, this x-axis is like the base of the vessel, and the y-axis is like the height of the vessel. Excuse me. Okay. And what you do, you erect some bars. Okay. All these black ones are some bars. Okay. Of varying heights in the vessel. Okay. So let me say this entire chunk is my vessel. Okay. And inside the vessel, I have some different number of vertical bars, and the height of each bar is different. Okay. Now each bar is like one stream of the channel. What is the height of the bar is precisely given by this quantity, sigma square by sigma I square. Maybe I can write it here. So for example, this is sigma square by sigma RH. This is sigma square by sigma 1 square. For ith stream, it is the height of the vessel is sigma square by sigma square I. That is the height of the bar. Okay. Basically, I take a vessel and I know sigma square and sigma I square because that they are the noise power and channel component. I assume the channel is already known. Only then I can do the power allocation. Remember, so only of the unknown is that you need to optimize is the piece. Everything else is known to me. Okay. So the height of this each of the bar is given by sigma square by sigma I square. Now what we will do is we will pour water into this vessel. Okay. Now naturally, the bar which has the least height will start to get the water first. Okay. Every other bar basically will not get water first. As you keep pouring the water, basically you will get the bar with the least height will be the one which will get filled up first. Then the bar with the next least height will get some water. I mean, you understand, right? Maybe I will show another diagram. Let me explain it here. So suppose I have a vessel. Okay. So remember, this is sigma square by sigma 1 square. See, generally the notion is that sigma 1 is greater than or equal to sigma 2 greater than or equal to, and so on till that is the usual way of our description of singular value, right? So sigma RH. That is our decreasing order. That's how we define. Which means 1 by sigma will be the least value, because 1 by sigma 1 will be less than or equal to 1 by sigma 2, and so on till 1 by sigma RH. So multiply by sigma square on all sides. That means the bar of the first stream will be the least height. The second bar will be the second least height. The third bar will be the third least height. Okay, and so on till the last bar will be the sigma square, sigma RH. Okay, now in this kind of a vessel with all these bars, if I start to pour water, first this bar will get filled up. The water will stand above this bar. All these are solid bars. Okay, water cannot go inside it. The water will now start to get occupied in this region, and once this level is crossed, then the water will get occupied in the second bar also. Once this level is crossed, then the third bar, and so on till if you pour sufficiently large amount of water, then it's possible that the water level will keep increasing with all the bars being filled. And once all the bars are filled, if you keep on pouring more and more water, only the height of the water level will increase, but all the bars will remain filled up. Okay, is this description of water filling clear first? Can anyone confirm? Then we will see what is the power allocation.
Yes, sir.
Okay. Now the power allocation is exactly the water filled for the each of the bars. So for example, for the first bar, this is the power allotted. That is the water level that is above the first bar till the top water level. This is the top water level. Okay. The power, this is the power that you need to allot. So this top water level is what is 1 by lambda. That is the optimization problem. You have 1 by lambda, right? This 1 by lambda is this top, this particular top, this particular value is 1 by lambda. That is the top power level, top water level. The water that is standing on top of the first bar is the power allotted to the first bar, power allotted to the first stream. The water on the second bar is a second stream. The water on the third bar is a third stream. And so, but you see here for the ith bar, see that this bar is more than the water level. What does it mean? This is precisely the cases where if you compute the Pi star, it will become negative. So that means I cannot put any water on this bar, which means that stream will have a zero power. Okay, so wherever you have the bars going above the water, that is the bars are not completely submerged, though the streams corresponding to those bars will get a zero power. Wherever the bar is completely submerged, then the water that is occupying above that bar till the water level, the top water level, that particular water level is the power allotted to that particular stream. This is called water filling based power allocation. Is this clear?
That case where the power is more, so that channel doesn't have any power, zero power.
No. That's again a good point. You have told exactly opposite, because you see, let's again go back to this particular diagram. You see here, so among all these bars, which has the highest water level? Water. First one, right?
First one.
First one. But now you see, for the first one only sigma is a maximum. The water that you get for the last bar has the least, say, sigma I. That is sigma RH is the minimum singular value. That means the channel gain sigma I square is the channel gain of that particular stream. That is the minimum channel gain. So what this integral tells is, wherever there is the best channel, put more power in that channel so that you get more data rate from that channel. Whenever the channel state has dip a little small, the channel gain is small, don't give more power in that. Give less power. Basically, it's a greedy algorithm. Okay, wherever I feel that I can get more gain, give all my resources to that particular fellow. And wherever I see that, okay, this particular stream will not help me much, then okay, why should I spend more? It's like, kind of something like money you bet on some particular kind of object and so on and so forth. Whichever is going to give me a best maximum, I'm going to give more all my resources there. It's like that. Is it okay?
So where from this constraint like sigma 1 greater than sigma 2 that comes to?
This basically, this basically is the defining characteristic of SVD. If you remember SVD, we defined it like that. We define these singular values sigma 1 greater than equal to sigma 2 in the decreasing order, right? That was the definition of our SVD. So it's coming from there.
Okay. And how is it applicable in, let's say, in a wireless channel or something?
So in wireless channel, we have effectively converted our wireless channel into something like this, right? YA, it multiplies with sigma I, then it adds with noise N and gives, this Xi, this YI. This sigma I is the ith singular value of matrix H. This is the effective channel that the spatial multiplexing will do to you.
Okay.
So that's where the singular values are coming. So singular values will turn out to be the channel gain of every channel, every stream in the spatial multiplexing scheme. Okay.
Okay. So in that it's like the first channel has more power than the second power, like that.
Correct. Like that. In general, what will happen is if you want, let's say, shuffle. Let's say if this becomes, so that is the intuition. The intuition that you should always take away is it's not that only first stream will get the best channel, the maximum power. The second stream will get little less power. That's not the takeaway. The takeaway is the better channels will get more power. For example, suppose somehow I arrange my SVD in a way that I don't want to obey the decreasing order. Okay. I can always find an SVD such that I can, need not obey the decreasing order. Accordingly, I will make my U matrix and V matrix slightly changed. I can do that always. Then in that case, what will happen is your sigma 1 can be something, this sigma 2, what I'm trying to say is you can find, you can maybe get a case where your first bar is of height sigma square by sigma 1 square. The second bar is of height sigma square by sigma 2 square, where this is smaller height than this. Then you will put more power here than this channel. So the takeaway is that better channels will get more power. That is a takeaway. Okay.
Okay. Then the order gets changed.
Yes, order can change. See, it's like this: sigma 1 U1 V1 plus sigma 2 U2 V2 Hermitian. Okay, Hermitian. This you can write it as U1 U2 sigma 1 sigma 2 0 0 V1 Hermitian V2 Hermitian. Okay, you can also write the same thing as U2 U1 sigma 2 sigma 1 V2 Hermitian, V1 Hermitian. If you do the multiplication of both of these three products, you'll get the same answer. But you see, in this, if sigma 1 is greater than sigma 2, in this thing, sigma 1, the first entry is less than the second entry. You get it, right? You can always reshuffle your singular values and accordingly shuffle your U and V matrices, columns, and still get the same matrix. The final product matrix is H. But so then people ask, okay, what should I take as SVD? So just for a notational, consistency, we define SVD to be that particular thing where you get the decreasing order. That is wherever the matrix singular matrix such that sigma 1, sigma 2, something like this. Then sigma 1 is greater than or equal to sigma 2 greater than or equal, so on to sigma p. This is for the consistent definition of, because any definition should be consistent. It should not have any ambiguity. But when you apply that to our application, the sum is always interchangeable. You can x1 plus x2 or x2 plus x1. Both are same. In that way, you can always keep shifting the bars here and here. Then again, if that is the case, you cannot still argue that only first stream will get the maximum power. No. The takeaway is the stream which has the best channel will get the more power. Okay?
Okay, sir.
Fine. So,
Small question. Why we kept this power sum that constraint less than equal to P total? If you see, power should be always equal to what we say PT, not less than.
Correct. That's a very valid question. In fact, it turns out that if you solve this optimization problem, the optimal PIs will indeed, if you sum all of them, it will indeed be equal to P total. This is only for the mathematical, notation, mathematical consist accuracy. That's all. But if you basically solve for all these PIs, basically you will end up showing that these optimal PIs will be such that that is evident from this. You see, I'm finding the 1 by lambda such that this PI is summing to P total, which means if I sum all these PI star will be equal to P total only. Here I did not put less than or equal to. The reason why I put less than or equal to is little mathematical, because what happens is, for those of you who are aware, what happens is if you put less than or equal to, this constraint sets become something called convex set. Then this problem is what is called as convex optimization problem, because the objective function is a convex function, because I'm maximizing over a concave function, which is like a convex optimization problem. For a convex optimization problem, the solutions are easily derivable. But the moment you don't impose less than or equal to constraint, means you will have equal to, if you impose equal to constraint, that is no more a convex optimization problem for which the solution is very difficult to find. But good point about this convex optimization problem is, it so happens that the optimal point is such that where the optimal PIs, if you sum up, it will be equal to P total. It will not be strictly less than P total. Okay, is that okay? I hope that is clear. I didn't get a response. Okay, fine. So the height of the water above the IH bar in the vessel is the power for IH stream. Okay. Now the second, we are going little late, little slow. Maybe we will quickly now go over. The second point that was discussed was PCA via SVD. Okay. So this, I think, should have been little easier in the sense that we have already discussed PCA in the previous sessions. So here, basically, the idea is that if you remember what you do, you construct the covariance matrix and compute the eigenvectors of covariance matrix, right? So basically, your covariance matrix was exactly this X transpose X. Was exactly X transpose X. So finding eigenvalues of X transpose is same as saying compute the right singular vectors of the data matrix X. So that is the relation that SVD has to PCA. Okay. So again, how many principal components should you choose? In this particular context, professor gave the example of the best K rank or P rank approximation of any matrix X. Okay. That is basically, if you solve this optimization problem, if I have any matrix X, okay, this matrix may be full rank. For example, let's say X belongs to C to the n cross n. It's a square matrix of size n, and let's say X is full rank, that is rank equal to n. But I'm interested in one particular question: what is the best K rank approximation of the matrix X where K is less than or equal to n? Okay, what is the matrix X with K rank that can best approximate the matrix X that is given by X hat in this problem? Okay, so it can be solved as an optimization problem. That is, what is the minimum value of the error between X and X hat? That will basically tell what is the best X, right? That's because the best X should have the minimum error between X and X hat. The best X, which is X hat, that is minimization over the Frobenius norm square bit of the difference between X and X hat, subject to the constraint that the rank of the X hat, which is the best approximate for X, is equal to P. P rank approximation, this is called the P rank approximation problem, or the best P rank approximation problem of a matrix. Okay, and it's indeed achieved using the singular value solution to this X hat is equal to, given by the first P. It's like you take the first P left singular vectors of the matrix X, the first P singular values of the matrix X, and the first P right singular vectors of the matrix X, and then form this kind of a SVD, productify all of the three matrices. The resultant matrix is the best approximate for the matrix X with K rank. So this is a result in mathematics. So basically, if you compute the error in this particular term, you can show that the error is given by sigma p plus 1. That is the p plus 1, the singular value of the matrix X. Okay. Now, depending on p plus 1, whether the error that I can tolerate in doing the PCA, because PCA you do have some loss information, because I only want to capture the information of this particular data along the principal components. I don't want to capture the data along all the other components. Okay, so there is going to be loss in doing this. So what is the error that I can tolerate? If that error that I can tolerate is less than if the error that I can tolerate is going to be less than sigma p plus 1, that means I'm actually, by doing a p rank approximation, I'm going to incur an error. This is the error. I'm going to incur an error which is more than what I can tolerate, which means I need to go for I need to take one more principal component. Then I need to check sigma p plus 2. If this happens to be less than what I can tolerate, then very good. That means the error that I will get by selecting p plus 1 principal components is something that is less than what I can tolerate. So I'm okay with selecting p plus 1 single principal components. So this is the way PCA has linked with SVD. The third very interesting application that Professor had discussed was on DO estimation problems. It finds applications in radar target localizations, beamforming and communication systems, also source separation. Let's say there are two speakers in a room. They are talking at two different microphones, and you have, let's say, a lot of speakers. Okay, an array of speakers. The speakers will then give output of both the voices from the two persons microphones. Goal is to distinguish, okay, what is speaker X talking and what is speaker Y talking. I need to have some kind of an algorithm to separate both the sources. So those kind of problems are also well attacked using under the paradigm of DO estimation problems. Okay, let me describe the problem. So you have a point source, that is point source. The source is very small. Okay, and it emits some signal S of t, let's say. And there's a collection of sensors. There's an array of sensors. That's why it's called array. You have a collection of sensors or array of sensors. Let's say there are m sensors in the system, and all of them will receive the signal from a very far away. So this distance is very, very large. D is very large. Okay. In that case, all of them will come parallel to each other. All the rays will be parallel to each other. And these are the rays from the point sources. So now let's say the first sensor makes an angle theta with the reference axis. This is the normal axis, reference axis. The same ray will make an angle theta with at the second sensor also, because both these lines are parallel. And the last ray will also make an angle theta. But the difference is, if you see, the time at which the ray arrives at the first sensor will be different from the time at which it arrives at the second sensor. And the difference is given by this, because the ray has to travel this particular extra distance to the second sensor. For the last sensor, this is the additional distance that the ray has to travel. That's why if you see the signal received at all these sensors will have a phase shift, because they will all have some phase difference. They will have same amplitude, but the phase of the signal that is arriving at these sensors will be different because of having different propagation distances. Okay, so this theta is called the DOA, or the direction of arrival of the source at the array. So this kind of an array is what is called uniform linear array. That is basically I place all the sensors in a straight line, and the inter-elemental distance, that is the distance between the first sensor and the second sensor, is same as the distance between second and third, same as the distance between third and fourth, and so on till all. So inter-elemental distance is the same across the entire array. So that's why it's called uniform. It's called linear because you place them in straight lines. So it's a uniform linear array. So if you write down the received signal at the array at any given time, okay, because see, all these waves are arriving, this particular phenomena of capturing the signal is at a given time. So if at a given time instant, if you capture the received signal, it is given by y1 till ym, because there are m sensors. From every sensor you're going to have a data given by this vector times s. S is the common message that the source emits. So each of the entry of the vector represents a phase difference that every element will undergo. For example, the first will not undergo any phase difference because it is a reference. You don't have any extra. This is called the reference source, reference sensor. And this dotted line is called reference axis. Okay, so this is a phase shift. So the second element denotes what is the phase shift that the signal is going to undergo with respect to the first sensor, that is namely 1. The third element will tell what is the phase shift of the signal received at the third sensor with respect to the first sensor, that is the reference sensor. All these are captured by this particular entries. The last will have this particular sensor. So what is see the way these phase shifts are defined. First is called 2 pi by lambda times d cos theta. Second will have 2 into 2 pi by lambda. The last sensor will have m minus 1 into, there's going to be another 2 pi into d cos theta divided by lambda. This vector is called array steering response vector, and its parameters by 2 variables, namely m and theta. Let's say m is known. So then theta is what? Is an unknown variable. So it is a function of theta, right? So if you, and then n vector is the noise vector. Okay, so you can write y is equal to as plus n, where y is an m by 1 vector, a is another m by 1 vector, s is a 1 by 1 scalar, and n is another m by 1 vector. Okay. This y is called a snapshot because it's like you click a photo, whatever captures in that particular time instant will all be a part of the snapshot. So similarly, when these sensors receive the array, you click a photo. So at a given time instant, all of these sensors will have the signal, right? That is what is captured by this snapshot. So the geometry of the array decides the array steering response vector. Okay, one of the solutions to do a DO estimation, that is, if I want to know what is the theta at which this point is located, okay, that is called DO estimation. One of these solutions is basically given by music. Music stands for multiple signal classification. So basically, how does this mu from the first word is mu, si from the second word is si, and c from the last word. So this basically forms music. Okay, basically I'm trying to classify multiple sources or multiple signals with respect to their direction of arrival. Okay, so that's why I'm going to multiple source models, where I'm extending this particular scenario to a system with many point sources. Let's say I have let's say this is one point source, this is another point source, this is another point source, and so on. There are m sensors. All of them are sending signals at the same time, but all of them have different angles of arrivals or direction of arrival. Okay, goal is to estimate what is the theta. Okay, so basically in that case, your y is the sum of all the received signal from all the p sources. Let's say there are p sources. Okay, p far field point sources. P far field point targets or point sources, then this will be the received signal. You can collect all these vectors a of theta 1, a of theta 2, and so on till a of theta p in the matrix A, and collect all the signal messages or whatever from all the sources to be vector S. The noise is n. So you can write y is equal to as plus n. This is a vector equation for the received signal for a for p targets in the system. The goal is to find theta 1, theta 2, and so on till theta p. One solution is music. Basically, what it does is it exploits the orthogonality between the noise subspace and the space spanned by the array steering response vectors corresponding to true DOS. What I'm trying to say is the space spanned by this guy, AS, is the signal space. It's called the signal space. The space spanned by N is called the noise space. Okay. In general, signal spaces will be orthogonal to noise spaces. If you want, we can discuss about it a little more, but I want to finish certain things which were covered in class by professor. Okay, so AS plus N. So AS is called the signal component and N is called the noise component. The signal space defined as the column space of A, because A times X is something that lies in the column space of A. The column space of A, that is the column space of the matrix formed by all the array steering response vectors at two true DOAs, will form the signal space. And the noise space is just formed by the noise components. The music algorithm goes as follows. Music has to collect L snapshots. Okay, so y1, y2, and so on till yn, each of dimension m cross 1. Okay, with these ML snapshots form the sample covariance matrix, very similar to PCA. That is defined as this particular summation. Okay. Now, once you form the sample covariance matrix, do an eigenvalue decomposition. Again, similar to PCA. Do an eigenvalue decomposition U lambda U Hermitian. Okay. Now, this U, what is the size of U? It's M by M. This is also M by M. This is also M by M. So M by M matrix, right? U is a M by M matrix. Take the first P columns of the matrix U and call it as US. So it says US is a M by P matrix. Take the remaining columns, that is M cross M minus P columns, as a matrix UN. Now you can show that this particular US will span the signal space and this UN will span the noise space. Okay, but signal space is same as the space span be array steering response vectors. So the goal is, once you obtain US and UN, I know what UN is, then find the values of phi, that is the theta, such that a Hermitian of theta times UN, this norm goes to 0. Because a Hermitian of theta, whenever theta happens to be the true DOA, let's say phi naught, then this inner product will go to 0 because noise subspace is orthogonal to signal subspace. And whenever it goes to 0, there's going to be a dip in this particular function. Or if you take 1 by that inner product's norm square, there's going to be a peak in the function. Okay, but remember, I'm able to partition it as US and UN if by knowing P, because I'm getting the first P vectors of the matrix U as US. That means the music algorithm requires a knowledge of number of sources in the system. It's okay. I mean, I don't know the angles of arrivals of each of the sources, but at least I should know how many sources are present in the system. Without that, music cannot work. Now run the algorithm. So you vary your angle from minus 90 to plus 90 degrees, construct the array vector at this particular phi, and then run the spectrum. Find the pseudo, it's like this also called spectrum, or a function. S of phi is equal to 1 by this norm square. Whenever the phi equal to true DOA, this particular norm will go to 0 because that is where signal and noise subspace were orthogonal, and you'll start to see peaks similar to this. You see here, I plot S of A as a function of phi, and whenever phi equal to theta 1 hat, that is wherever you get a peak, call that particular angle as a theta 1 hat, all the estimates of the DOAs. Okay, so this is called the music algorithm. The last part was on estimation theory. In particular about linear minimum mean square error. That is, it's called LMMSE estimation. So the goal of this kind of problem is, let's say there's a parameter, say X. There's some parameter complex, it could be complex number or it could be real number, no problem. Some parameters X is there, but I don't know what that value of the number is. Suppose, but I have a noisy observation of the number X, or I call parameter X, given by Y is equal to X plus N. That is, the actual value X is perturbed, or it is, you add some noise over it, and then I get to see what my Y is. Then the problem of estimation theory is, given Y, recover or estimate the value of X. This is the goal of estimation theory. Okay, so estimation theory uses the fact that this unknown parameter X and the observation Y are correlated, meaning that if you remember long back we were discussing about correlation. What is correlation? The knowledge given by the random, if there are two random X and Y, okay, the knowledge that is said about the random variable X when the knowledge of Y is known to us. Okay, if I know Y, can I tell anything about what X is? That was called that basically was quantified by the correlation. So the same principle here also. If I know Y, can I tell you what X is? If only if X and Y are correlated, can I do that job? Otherwise, I cannot do that. Right? So estimation theory, very at its finest level, uses the fact that the observation and the unknown parameter have some non-zero correlation. Okay, now this is about basic estimation theory paradigm. Now, one kind of estimator, one class of estimator is called LMMSE, MMSE estimator. It's as it's called, it's linear MMSE estimator. What does linear mean? It's a linear function of your observation y. That is why it's called linear. Okay, maybe it's not theta. I meant to say it is x. It's x hat. Okay, any estimate I use the letter hat to denote, because I really don't know whatever I guess is actually the true value itself. So x hat is the estimate of x. Okay, so linear estimator is that kind of an estimator where the estimator is a linear function of the observation. Okay, so here, for example, see this. Okay, here I have written the vector matrix equation. For example, if you consider everything to be in one-dimensional scalar, x hat is equal to c times y, where c is some number. So it's linear scaling of your observation. That's why it's called a linear estimator. Now, how to find the c? That is the second part of the acronym MMSE. The MMSE states that it's the average value of the means. So basically MMSE, right? It's minimum mean square error. So it is minimum mean square error. Okay, so that means, what is a minimum? What is minimum? This minimum is captured by this particular quantity. What is mean? Captured by this E operator. I told you long that E will take the average. That's why it's called mean. What is square? This particular 2 is a square. What is error? This difference between x and x hat. That is the difference between what I have guessed about the parameter and what is the true value of the parameter. I take this is the error, take the square. So means this is called squared error. Take the mean of across all possible realizations of x and x hat. That will give the mean square error, and minimize the mean square error. That is the minimum mean square error. Okay, this is the actual, it's called MMSE estimate. It's called minimum mean square error estimate. But if I impose a condition that on top of that the estimate should be a linear function of y, I get a constraint subject to x hat equal to cy. This is called linear MMSE estimate. Okay, in general MMSE and LMMSE estimates can be different. They can also be same under some conditions. Okay, but linear MMSE is a subset of all the MMSE estimators, which has a linear function of the observation y. In general, MMSE can be a linear or non-linear function of y, but LMMSE only restricts that class of estimators, which is a linear function of y. Okay, if you solve for this optimization problem, you can show that your C matrix turns out to be this particular matrix. Rxy times Ryy inverse, where Rxy is called the cross covariance of the parameters x and y, and Ryy is called the autocovariance of the vector y. Okay, so if you substitute for this C in your estimator, x hat is equal to cy, you get x hat is equal to Rxy Roy inverse times y. This is the MMSE estimator of the vector x given observation y, if x and y are zero mean. I think in the class professor also mentioned how to basically get, if it's non-zero mean, you need to tweak. Maybe you need to make y minus mu y and add plus mu x. If x and y are non-zero mean, you need to appropriately perturb. Then the error in LMMSE is given by basically substitute this x hat in this objective function. That is basically this. If you expand it out, you get this particular error covariance. Okay, this is called the error covariance matrix. Okay, so I think we took today very elaborate discussion on just revising the lecture today. So what I will do is, at 7 o'clock, I will solve one problem and then we'll go for break. Okay, question 1. Consider a spatial multiplexing based MIMO system such that the rank of the matrix H is equal to 4. let the non-zero singular values of H be given as sigma 1 equal to 4, sigma 2 equal to 3, sigma 3 equal to 2, and sigma 1 equal to 1. Okay, so I have given you, there are four streams. That means this is a spatial multiplexing system with 4 streams, and I've given you the singular values, that is the channel gain of each of the stream. Let the total power be P with noise power equal to sigma square. It is the noise variance or noise power. Find the conditions on the total power, that is P, such that the power under water filling is allotted to A. All 4 streams, B. Only 2 substreams, so only 2 streams, or maybe I'll take one stream, and C, only 2 streams. You understand the question? So basically, in essence, what I'm saying is, I should, how much power P should I put so that in one case, all 4 streams will get some power. In second case, only the one stream will get the power. In the third case, only 2 streams will get the power. Meaning, indirectly, if you go to water filling example, the base interpretation, what is the amount of water that I should pour so that all the 4 bars get some water? One stream means only 1 bar should get water. 2 streams means only two bars should get water. And exactly 2 bars only should get water, not less than 2. And not more than 2. 3 bars should not get water. That is the equivalent translation. Okay, so let's solve this problem. If you please ask me if you have doubts in the question first.
No, so it's clear.
Yeah, thanks. So we know that, recall that sum rate in SP means spatial multiplexing. Okay, is given by summation over I equal to 1 to R of H log base 2 of 1 plus pi sigma I square by sigma square. Okay, subject, this is the sum rate in the SP system. Then optimal power allocation is, what is optimal PA star? Given by
1 by lambda tilde.
Correct. Sigma square by
sigma I square plus.
Correct. Okay. Now the first question says, what should be the condition of the transmit power P? That is, P is the total power. Our P tot that we wrote in the optimization, right? That is this P. Maybe I can write the same notation. P tot. Okay. So now what should be that P tot so that all 4 streams will get power? I'm not going to do it mathematically. I'm just going to use the water filling interpretation and solve this problem so that we know, as engineers, we should also use intuitions to solve all problems. So I'm just going to draw the diagram. Okay. So, okay, let me write down. What is sigma 1 square? It is 16. Sigma 2 square? 9. Sigma 3 square? 4. Yeah. And sigma 4 square is 1. Okay. Now, so then if you draw the diagrams, this is what? Sigma square by 16. The next bar will be sigma square by 9. See, Sigma square by 9 is little more than sigma square by 16 because denominator 16 is more than 9. That's why second bar is little larger than the first bar. The third bar is sigma square by 4 and the fourth is sigma square itself. Okay. Now the question is, I need what is the P tot so that all the 4 will get power. What does it mean? I need to ensure that I need to put sufficient amount of water so that all the bars are submerged. This is equal to P1 star, P1 star. This is equal to P2 star. This is equal to P3 star. And this is equal to P4 star. And all P1 star, P2 star, P3 star, and P4 star should be greater than or equal to 0. Okay, so this is the first condition. Solution to the first so question should be something like this. So then what does it mean? This is a condition. So then what does it mean? It means summation over Pi star equal to P tot. That is our constraint. So I is equal to 1 to 4. So what is this top water level? This is equal to 1 by lambda. Correct? That means if you expand this is nothing but summation over, or maybe this is nothing but 1 by lambda minus sigma square by 16 plus 1 by lambda minus sigma square by 9 plus 1 by lambda minus sigma square by 4 plus 1 by lambda minus sigma square should be equal to P tot. Okay, so this is nothing but saying 4 by lambda minus sigma square plus sigma square by 4 plus sigma square by 16 plus sigma square by 9 should be equal to P tot. Okay, if you compute this, you can show that your 1 by lambda will be equal to P plus, I've just done the calculation of offline, so I'm just writing it down. P plus P tot, okay, P tot plus 1.43426 sigma square by 4. Okay, that means this should be this is the, what is this? Total top water level, because it is 1 by lambda. Now this top water level must be such that it is greater than the tallest bar in the vessel. Correct? That only under that condition can I give all the power to all this. Can I give the power to all streams? Is that correct or not?
Yes, sir.
Correct. So I'm just going to, that means, but the tallest bar's height should be less than top water level. What does it mean? What is, okay, I know what top water level is. What is the bar height of the tallest bar here?
Sigma square. So 1 by lambda greater than sigma square.
Exactly. 1 by lambda should be greater than sigma square. But I know what is 1 by lambda already here, right? From 1. If I call this as 2, from 1, I know the value of 1 by lambda from 1. Says P tot plus 1.4236 sigma square by 4 should be greater than sigma square. If you solve for this inequality, you will show that your P tot must be greater than 2.576 sigma square. So this is a condition that your total transmit power should satisfy, so that all the 4 streams will get some non-zero power. Okay, fine. Now let's see the second question. That is, only only one of the streams should be filled. Okay, now let me draw the diagram. Now my question is, you tell which of the 4 streams should be filled.
First stream.
Yes.
First stream.
Exactly, because if I pour water will start to fill this only naturally. right? And I'm saying that only that should get the water, that should get power. That means I should not pour more water so that this will also get power. I should only pour that as much amount of water needed to just fill this particular height. Correct or not?
Yes.
Yes, that's what I'm going to use now. So if you basically compute again, basically what I'm trying to say is this should be your 1 by lambda, because that is the total water level. The top water level should be equal to one at max this. It cannot go beyond this. If it goes beyond this, then this will also start to sigma square by 9 bar will also start to get some non-zero power. Okay, so your 1 by lambda cannot go beyond sigma square by 9. Correct? So that is first condition. First condition, 1 by lambda is less than sigma square by 9. Okay, but what is but basically what is your power? Pi is what?
P1 equal to P dot.
Exactly, P dot. But what is 1 by lambda is equal to? P dot plus sigma square by 16, correct? And just
Yes.
this is a sum of this plus sum of this. That means what does it mean? P dot plus sigma square by 16 should be less than sigma square by 9. Correct? That means P dot should be, you can show that this is given, this if you just subtract these two quantities, you can show that this is given by this. And also it can be equal to 0. If it's 0, what does it mean? There's no power anywhere. So it should be strictly more than 0. Okay, so basically what will happen is, as you keep increasing your transmitter from 0 to 7 by 144 sigma square, this bar will slowly get filled up. And the moment you reach a total transmit power of 7 by 144 sigma square, you would have reached this point. If you give any more power, the second bar will also start to get some water, which means that will also get some non-zero power. Okay. Now the third question, which is the last part of this question. I need only two subcarriers, or sorry, two substreams. Sorry, two streams. Okay. So let me draw the diagram. Sigma square by 16, sigma square by 9, sigma square by 4, sigma square. Now tell, where should the top water level be if it's two stream?
1 by lambda less than sigma square by 4. And then
Correct.
P1 plus P2 equal to P2.
Exactly. That's all. These are the two equations, and you have correctly found out the equation. This should be the maximum 1 by lambda. Okay. So the first condition is 1 by lambda must be less than sigma square by 4. First condition. The second condition is your summation over, or maybe I can directly write y summations. Your P1 star plus P2 star equal to P dot. But your P1 star is but 1 by lambda minus sigma square by 16 plus 1 by lambda plus sigma square by 9 equal to P dot. Okay. From this second equation, from 2, you can show that your 1 by lambda equal to 144 P dot plus 25 sigma square by 288. I'm just doing mathematical manipulations. Okay. Okay. But from 1, what is it? 1 by lambda should be less than sigma square by 4. But from 1, first equation, 1 by lambda is less than sigma square by 4. Let's substitute this quantity here. Implies 144 P dot plus 25 sigma square divided by 288 is less than sigma square by 4. This implies P, you can show that if you solve this, you will show that P total less than 47 by 144 sigma square. Okay. Is this correct? Is this complete?
0 greater than.
Sorry, yeah, repeat it.
0 greater than P dot less than 47 by 144.
Okay, so you're saying this, right? Correct? You're saying this, sir?
Sorry. It won't be 0. It will be greater than sigma square by 9.
Sigma square by? Sorry, sigma square by?
9.
9. Why 9?
So
No,
that
this is not 1 by lambda. This is P tot. Your sigma
Okay.
square by 1 by lambda is not P tot, right? But you're actually your thought process is correct. The thing is, I cannot put 0 here because if I come below the if I reduce my transport so much, then only one will start to fill. The second will not fill at all. Right? So what you should do, go back to the first question. So as long as P tot is less than 7 by 144 sigma square, I will have only the first substream to be filled. Correct? So I should have at least 7 by 144 sigma square as the P tot, so that my first, I will even move to the second stream water filling. Correct?
Yes.
So that means, now can you tell what's the answer?
7 by 144 sigma square.
Correct. Great. That means you should have a minimum total power of 7 by 144 sigma square, and you can maximum you can have a power of 47 by 144 sigma square, so that exactly 2 of the streams can be allotted with power. Okay.
Yes.
Fine. So are there any doubts in this question?
Sir, no doubt. But sir, last time you said ki you will take music in circular array also. If 5 minutes you can give that after the break.
Yeah, sure. So today I will solve. That's a next question. I will solve that. Don't worry. I remember that. I will solve that today.
Because sir, practically I have already seen that DOA antennas are in circular fashion, either 4 or 6 like that.
But actually, while it really depends on the application. For example, even I have seen circular array of microphones. But if you see traditional app, if you go to a tower and if you see the kind of deployment they do, it's not necessary that they should always do a circular type of array architecture. They can always go with the linear array, like what I showed, uniform linear array, or something called planar array. Planar array means you take an entire rectangle surface and embed sensors everywhere in both x and y dimension. Okay, this is called a planar array. So it basically entire rectangle is full of arrays. Linear array was just along one straight line you put an array. Your circular array is basically take a circle and then place the sensors on this particular circular fashion. But there's something called planar array where you take a two-dimensional grid and put and embed all the sensors in there. It's called planar array. So all these kinds of arrays are well deployed. It depends on the application, where you want to use what. Okay, but nonetheless, the uniform circular array is there. That's the next question that I will solve today. Yeah, so maybe it's 7:19. Let's come back at 7:24. Let's take 5-minute break. Okay, so it's 7:24. Can you hear me and see my screen?
Yes, sir.
Okay. The second question for today's session is design music algorithm for an uniform circular array. Okay, so again, circular array means you have a circle, and on the circle boundary, you embed some sensors. You place the sensors. And what is uniform? That is, you place a sensor such that inter-elemental distance on the circle is constant. Okay, I will describe the theory and then I will write down. Okay, now let's consider M sensors to be arranged in a circular fashion with a radius of circle equal to R. Okay, what does it mean? Basically, maybe some other color. Okay, I take a circle, I draw a circle, and then I place the arrays, sensors like this. Okay, this is called a uniform circular array. Let's say this arc distance is d, then this will also be d, this will also be d. Between any two pair of two sensors, the distance is same. That is called uniform. That's why the term uniform is prefixed to the circular array. Okay, let the ith sensor measure an angle of I times 2 pi by m as shown. Let me draw what is this. Again, I draw a circle. Sorry for my circle, it's very bad. We'll draw a better circle. Maybe a little better. Okay, so if you remember, for an array, there are two things. One is called the reference sensor, or reference point rather. It's the reference point and a reference axis. Like in a linear array, what we do, the first sensor itself we took as a reference point, and this y-axis we took to be the reference axis. So similarly, for a circular array, we are going to define the center of the circle as a reference point. Okay, and we will just put a sensor there only to measure what is the signal at the reference point. And this x-axis is the reference axis. Okay, now I will have so many, let's say ith sensor is somewhere here. Okay, ith sensor. What is the angle made by the ith sensor with the reference point, with the reference axis? This I call it as I times 2 pi by m. That's because the first sensor will make an angle 2 pi by m. That is the so if you take the angle subtended by any small arc in a uniformly spaced circle is basically 2 pi by m. That's why the first sensor will make 2 pi by m, or maybe I could say, maybe I will say like this, not even first sensor. Maybe if I place the first sensor on the x-axis, this reference axis, the first sensor makes 0 angle, right? Second sensor maybe takes 2 pi by m. But if we say ith sensor makes I 2 pi by m, then that means implicitly assume that I don't make a sensor on the reference axis. I make the first sensor to make 2 pi by m angle. That means this is my first sensor. This makes an angle 2 pi by m. My ith sensor makes an angle I times 2 pi by m. Okay. Therefore, if you see, okay, there should be, I should have, just a minute. Let's see if this works. Oops. Okay. So ith sensor. Okay. If I consider source points, let's say here source. Okay, there's a source here. This will have a signal that will reach the reference point here, but it will reach this ith sensor here, right? So basically it covers an extra distance of this much. It's an extra distance. Similar to our ULA, right? Similar to our uniform linear array, we had that with respect to the reference point, the second had some extra distance coverage. But here, the reference point is the reference with respect to the first sensor, the reference point is having extra distance. Or in other words, with respect to the reference point, the first sensor is having lesser distance. Okay, right? So that means what does it mean? Let's say, okay, maybe let me write down. Therefore, the signal traverses, means it propagates. It's called traverses extra distance to reach the center of array. That is the reference point against the ith sensor. Okay.
Sir,
Hmm.
here radius is much less than the distance of propagation.
Correct. So that'll ensure that you are in the far field assumption. Means
okay.
very far.
Mm.
Maybe yeah, I can write that down. No problem. Radius is r is much less than d. No problem. Against the ith sensor. Okay. Now this extra distance, call it as di. Okay. Call it as di, or maybe not di because I'm using d to represent maybe some other letter si. Okay. Then what is the extra delay? Equal to tau I is equal to si divided by c, where c is the velocity of light. But this si, you can do some, this is a right angle triangle. This basically is your r. This small thing is your r. This distance is r basically. So you can do some, trigonometry and show that, and this is exactly your theta. Okay, maybe this is your theta. You can show that from trigonometry. This is given by r by c cos of theta minus I2 pi by m. That is theta minus I2 pi by m is this small angle here. Okay, and use the trigonometry in that triangle. You can show that this extra distance the delay or the extra distance si is given by r cos of theta minus I2 pi by m divided by c to get the delay. Okay, therefore,
what is theta here?
Theta is the angle of the DOA of the source.
Okay. Yes.
Okay. Therefore, if reference sensor receives x of t is equal to s of t, then the ith sensor receives xi of t is equal to s of t plus tau I. That is, it receives the signal ahead tau I seconds ahead of time. Okay, that is nothing but s of t plus r by c cos of theta minus, I'm just writing what is tau I is, okay, I2 pi by m. For narrowband signals, okay, this is maybe for those of you who know this, no problem. Otherwise, don't worry. Narrowband signals are those signals where the bandwidth occupied by the signal divided by the carrier frequency in which they're operating is much less than 1. Okay, but nonetheless, for narrowband signal, you can approximate this S of t as S of t into e power j 2 pi f r by c cos of theta minus I2 pi by m. Basically, what I did is I took this extra term, I wrote it in this fashion, multiplied by j2 pi f and raised it to the power e. Basically this extra delay will cause a phase shift of this much. The delay will translate to a phase shift for a narrowband signal. Okay, but what is this? What is the x of t? S of t is nothing but x of t, right? See from here. That means xi of t is equal to
Sir,
yes.
shouldn't it be e power j 2 pi f t in bracket t plus r by c cos?
No. That will basically come in that will the s of t will come here. That t will not come there. That's what I'm saying. For a narrowband signal, you can work it out.
Okay. Yes.
Yeah. R by c cos of theta minus I2 pi by m. Okay, so this is exactly like our ULA, right? For ULA, we have xi of t is equal to x of t into e power j2 pi by lambda into I minus 1 into t cos theta. That's what we had for ULA. Now we have, instead of that, this you have some other term here. So that means therefore your array steering response vector of UCA, what is given by A underscore UCA of theta is equal to e power j2 pi by lambda or cos theta e power j2 pi by lambda or cos of theta minus 2 pi by m, and so on to e power j2 pi by lambda or cos of theta minus m minus 1 2 pi by m. Okay, this is my array steering response vector for a UCA. Okay, now music is now straightforward. It's actually same as ULA, except that in the spectrum function, instead of AULA, you will just use AUC. Let me do. First step is collect the snapshots from t equal to 1 to L. L snapshots, same as what we saw for ULA. Second step is form your sample covariance matrix R hat equal to 1 by L summation t equal to 1 to L y tilde t times y tilde t, or maybe I will directly write here yt minus mu into yt minus mu Hermitian, where mu equal to 1 by L summation t equal to 1 to L y of t. Third is do eigenvalue decomposition of r hat equal to u lambda u Hermitian. Identify the noise space basis, namely un. It belongs to C to the m cross m minus p. Now for I equal to maybe phi equal to, maybe I'll write, wait. Run the following. For phi equal to minus 90 in steps of 1 degrees to plus 90 degrees, compute S of phi equal to 1 by un, that is the noise subspace you identify, okay, un here, times a UCA of phi. That's all. This is the only difference. Okay, and and phi hat I equal to 1 to p equal to argmax. See, again I'm using argmax. Now I think you will know what I mean. Wherever all the phis for which you get a maximum value in S of I, that is peaks, or the DOAs, gives DOA estimates of targets. Okay, so I think is this clear? There was a person who asked about music DOA. Is this clear?
Yes, sir. Yes, sir.
Sure. Okay, so we have 20 more minutes. I would like to solve one nice question, and then I would like to go over some practical radar problem. Okay, so I will just divide 10 minutes each. The next question, which is question number, okay, only we did 2 questions today, no problem. Question 3. Okay, so it's called clutter mitigation in radar systems. Via Kappan minimum variance beamforming. Okay, so basically radar is basically a system which is used to detect for targets in the environment. Okay, so maybe let me use a new ink. So radar is used to detect targets. Okay, let the actual target be at an angle, have a DOA, maybe have direction of variable DOA of theta1. Let the clutter, I'll tell what a clutter is for those of you who are not familiar, have a DOA of theta2. So clutter can be imagined as, for the purpose of in the case of modeling, as a noise. Okay, in addition to receiving a signal from the actual target, you also get some noise present from some other sources from some other angles. But accidentally you should not mistake and say that, okay, look, at theta2 also there is a target. No, that could be some noise. That could be any noise. It is not at the desired target. So all those sources which are undesirable to us are called as clutters. I would say undesirable sources. Okay, so I want to generally I want to mitigate or minimize the responses from the clutter, but I want to maximize the response from the actual target. That is the goal of this problem. I want to mitigate the clutters, and the solution for this is called as Kappan minimum variance beamforming. It's a very well established technique which radar people use. So I want to basically illustrate how this problem is formulated and what is the solution. Okay, so basically let me draw the diagram. So I will do some kind of beam forming. Okay, so basically the goal is design a beamformer okay that maximizes the response in theta1 direction and minimizes the response in any other direction. I took particularly theta2, but the clutter is something random. It's something like noise. So you can't say that it is only in theta2 direction. It could be anywhere in the space, right? So say theta2. It's not exactly theta2. So any other direction, I should minimize the response of the array, but I should maximize the response of the array in the desired direction where my actual target is located. So what do I mean by this physically? Let's say I have a big array. These are the sensors. Okay, and let's say I have theta 1. Okay, maybe desired source. And I have a clutter here. Let's say at theta 2. This desired source at theta 1. So I receive the signal at every sensor. I multiply it by weight W1, weight W2, and so on till weight Wm, where m is the number of sensors or antennas, whatever. Take the output and then combine them. Take the output set. The Z should have the component of only desired source, and all the components along any other direction should be as minimum as possible in the Z. Okay, so I need to design basically all these weights. I need to design these W1 through WM, W1, W2, and so on WM, such that the component of the desired source should be maximum Z, and in Z there should be minimal contribution from any clutter at any other direction in the space. Okay, let's write the received signal first. Received signal array is given by, it's like a multiple target problem. Y is equal to a of theta 1 S1 plus a of theta 2 S2, where theta 2, let's say clutter is at theta 2 direction, plus noise is n. Now, the beamformer response in theta 1 is given as W1, the W is basically the vector of weights, okay? W Hermitian A of theta 1. Similarly, the beamformer response in theta 2 direction is given as W Hermitian A of theta 2. It is the inner product of the beamforming vector and the array vector corresponding to theta 1 is beamforming response in theta 1. Similarly defined for theta 2. Now, we want to minimize the power of W Hermitian theta 2. So can anyone tell me what is the minimum value of this inner product W Hermitian A of theta 2?
0.
Yeah, correct. When is it achieved? Yeah,
When they are
get...
orthogonal.
No, I just said W equal to 0. Correct? But if I said W equal to 0, even the first thing, like this will also go to 0, right?
Yes.
So W equal to 0 is not the correct strategy. You can't say W equal to orthogonal because it might also minimize from this also, right?
Yes,
I mean, so you can also minimize the response from desired direction. So that's why what you need to do is you need to formulate an optimization problem. Let's write on the optimization problem. Okay. So problem. Therefore, what we'll do is, maybe I'll write it down. But this will also minimize the response in desired direction. Therefore, impose a constraint. Simple. Impose a constraint in desired direction. W Hermitian A of theta 1, let's say equal to 1, maybe just a number. Okay. Therefore, the optimization problem is minimize the function W Hermitian A of theta 2 square. This is basically the, I want to minimize this particular response, that is response in the undesirable direction with respect to overall set of W's, such that you still maintain a response, a very non-zero response in your desired direction. Is this clear?
Yes. So one doubt. Instead of this, why can't we write maximize W Hermitian A theta 1 and such that W Hermitian A theta 2 equal to 0?
You can't do equal to 0. What you can show is at less than some very small number epsilon.
Yes.
Yes, that's also very valid problem. That's also very valid problem. No problem. You can maybe what you can do, you can solve it and check, and you can maybe tell me the next class. Let's call this as P0. Call the other one P1. Max over all W Hermitian A theta 1 square subject to W Hermitian A theta 2 less than some number epsilon. Okay, maybe what you can do, you can solve both of them independently. I will solve today this problem. You solve it this problem, and we can compare the results and see what are the implications of the solutions.
Yes, sir.
Yeah, sure. Okay, so now let's go to solution to P naught. But you see hello, am I audible?
Yes, sir, you're audible.
Sorry,
the screen is not visible.
Yeah. Now it should be visible. Okay.
Yes.
The solution to P naught. Now, before going to solution to P naught, you remember I assumed that clutter is at theta 2 direction, but clutter can be in any direction, right? It's not you a priori you don't know that clutter is in theta 2. This was for the sake of problem formulation I came till here. So generally, but clutter can be at any direction. Therefore, P naught generalizes to the following problem. I will write on the problem and let's see if it's okay. P3 minimize over W. W. W Hermitian Y square subject to W Hermitian A of theta equal to 1. What I'm doing is I want to minimize my overall output power itself. This is Y is the total array output subject to the constraint that the power in the desired direction alone should be equal to 1. You understand? So what this means is no matter in any direction, wherever the clutter is located, I'm going to minimize the power from every other direction except the direction of theta 1. Is this clear?
Yes, sir.
Yeah. So this is the general problem. Okay. Now solution to P3. Okay. Another thing is, since the W is actually random, so what I'll do is I'll do an expected value, because not W, sorry, Y is a random parameter. All observations are in general noisy. So I will include an expectation operator to denote that I want to minimize the average power of the array, output power of the array, subject to the constraint that the energy in the desired direction theta 1 is equal to some constant fixed number. Okay, so now let me I'll solve this problem. Before that, I will do simplify I can simplify this number better. So W Hermitian Y is a number, right? This can be written as expected value of W Hermitian Y into W Hermitian Y conjugate. Correct? This is nothing but expected value of W Hermitian Y into Y Hermitian W. But W's are not random. Okay, this is nothing but W Hermitian into expected value of Y Hermitian into W. But what is this? This is our correlation matrix, right? RY W. Okay, so therefore P3 is same as the problem. P3 is same as minimizing W Hermitian RW over all W subject the constraint that W Hermitian A of theta 1 equal to 1. Maybe mod. Maybe mod is not necessary in case they, basically I'm not now talking about the energy itself, because if you see my actual response is that did not have energy. So I will write if this is satisfied, this will also be satisfied. Correct? That's why I'm removing the mod for time being. Okay. Is this clear?
Yes, sir.
Yes.
Yeah. Sure. Okay. Now let's just solve this problem. What is the problem? You need to solve using Lagrange. Solve by Lagrange. Lagrange multiplier. They call it as method of Lagrange multipliers. That is L equal to W Hermitian RW plus lambda times W Hermitian A of theta 1 minus 1. That is W is the objective function. This is your Lagrange parameter, and this is your constraint minus 1. Right? So now what should we do? We need to differentiate this with respect to W. Now, the last time I told how to take gradients and all those things. Can anyone tell me what is the gradient of this W Hermitian RW?
2W.
2WR.
Great.
WR.
It's just 2 RW, not 2WR. It's RW. Okay. Now, here it is lambda times. What is this? Just A of theta. Correct one? Correct?
Yes.
And this should be equal to 0 because that's what our gradient should be equal to 0. That is our first order necessary condition for any optimization problem. Basically, differentiate equal to 0. That's what I've done. So what you get here implies RW is equal to minus lambda by 2 into A of theta 1. Okay. Or W equal to minus lambda by 2 into R inverse of A of theta 1. Is this okay?
Yes.
Okay. Fine. Now, pre-multiply by A Hermitian of theta 1 on both sides. That is A Hermitian of theta 1 W equal to minus lambda by 2 into A Hermitian of theta 1 into R inverse A of theta 1. Okay. Now, can anyone tell me what to do?
Take permission on both sides.
Sorry, take Hermitian. No. See, what is this?
Reinforcements.
This is 1, right? That was our constraint.
Yes.
Yeah. 1 equal to minus lambda by 2 into A Hermitian theta 1 into R inverse A of theta 1. So now what is this? Let's analyze this a bit. This is a 1 cross M vector. This is M cross M and this M cross 1. So this is a scalar. Okay. So then I can get lambda equal to minus 2 by A Hermitian theta 1 or inverse A of theta 1. Okay. This let's call equation 2. So now you see equation 1, W equal to minus lambda by 2 into R inverse of A of theta 1. The only unknown is lambda. I got lambda in equation 2. So put 2 in 1. That is W equal to. So I'm just writing what is lambda. Okay, just lambda. Minus half times lambda, right? So I'll write minus half into lambda is minus 2 by A Hermitian theta 1 R inverse A of theta 1 times R inverse of A of theta. A of theta. R inverse of A of theta. 2 cancel, minus minus cancel. Therefore, W opt, that is the optimal beam forming, is given by R inverse of A of theta 1 divided by A Hermitian of theta 1 R inverse A of theta 1. So this is also called the Capon minimum variance. Why is it called minimum variance? See, variance in general measures the power of a signal. And I'm minimizing the entire power of the output signal, but subject to the constraint that I should maintain some fixed power in a given desired direction. This is called minimum variance beamforming. Okay. So this, if you apply this, so this beamformer, you can ensure that except for theta 1, the power, the sum total power from any other direction will be minimized as minimum as possible. Okay, so I think it's 8 o'clock. I actually wanted to discuss a research paper on DO estimation in the case of target. Like, how can you use the concepts which we studied in music and so on and so forth for a radar target localization. I just wanted to go over the research paper, but I think we are running out of time. So maybe next session, I will start with DOI research paper, and then I will basically move on with the questions for the next session. So next session, I will be focusing only on LMMSE estimations and only applications of where how you can use LMMSE estimators in different contexts.
Yes.
Okay. Yeah. Is there any doubts or questions on today's class?
No, sir.
Okay. Fine then. So then we can stop for today.
So next week
Maybe
is Vinayaga festival. So will you be still conducting